Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, you are going to learn how to simplify trigonometric identities. Now, this is the first lesson in our chapter for analytic trigonometry. Now, as far as what is a trigonometric identity, we're going to get to that in just a second. But in this lesson, these are notes that I gave exactly to my students inside of their own classroom. We're going to learn how to simplify basic identities, how to simplify trigonometric expressions using identities, as well as how to apply operations with trigonometric expressions. So to kind of get into the idea of an identity, basically all an identity is it's an equality relating one mathematical expression to another, and that's going to be equal for any given variables for all the variables. So just to kind of recap, you're actually very familiar, or you should be at this stage of the game, very familiar with identities. For instance, if I gave my students these, 5 equals 2 plus 3. That is a mathematical identity. The left side is equal to the right side. Now, as far as another mathematical identity with, some variables here, we could say, e to the x equals, oops, what am I doing? E to the x. The example here, I could say the absolute value of x is equal to the square root of x squared. All right, so this is a mathematical identity, the absolute value and then the square root of x squared. And what you can see is that the values of x or the equation is equal no matter what the value of x is, right? So if you're taking the absolute value of a number, or if you're squaring it and then taking the square root, the left side is always going to be equal to the right side. However, there is also another identity that you are familiar with that we're not really going to be dealing with in this section, but that is the idea of a conditional identity. For instance, I gave my students x squared is equal to 1. So this identity is not true for every value of x. It's only true for a given number of value of x. For instance, -1 and -1. And positive 1. So the way to solve a identity like this, we would actually solve for x squared. So therefore, we'd square root both sides, and we get x equals plus or minus 1. All right, so then what I did is I gave my students the idea, and I say, all right, let's go ahead and see if you guys can identify some identities for tangent of theta. So when introducing my students to how to identify the identities for tangent, what I did is I just kind of reminded them is where'd tangent come from? What does tangent represent? And remember, tangent just represents the ratio or the comparison of the opposite side over the adjacent side. And just from there, we can actually identify our first identity because, again, we have an opposite, we have an adjacent, and we have a hypotenuse. So tangent represents the comparison of how big the opposite side is compared to how big the adjacent side is. And just remember, you also have sine, which is opposite over hypotenuse. You have cosine, which is adjacent over hypotenuse. And then you have your reciprocal identities, which was the cotangent, which is adjacent over opposite, cosecant, which is hypotenuse over opposite, and secant, which is hypotenuse over adjacent. But the important thing I said was cotangent is the reciprocal, right? So what that means is if I flip tangent, then I'm going to get cotangent. So if I flip cotangent, or basically put it under 1, that's going to be equal to tangent. So that is my first identity here. 1 over cotangent of theta is equal to tangent. And again, you can kind of think about that in terms of fractions, like if tangent is opposite over adjacent, and cotangent is going to be adjacent over opposite, right? Well, if you divide it by a reciprocal, that means you're going to multiply it by its reciprocal, so it ends up being opposite over adjacent. So you can see that that is our first identity. Now, to understand our second identity, we needed to get a little bit more advanced just from a random triangle in space. So what we did is we put our triangle and a xy axis. And so what that allowed us to do is say, well, if this is on an xy axis, then really this side length represents an x value, and this side length is going to represent a y value. So therefore, this point right here represents an x comma y. And then r represented the distance that point is away from the origin, also known as the hypotenuse of the triangle. So therefore, we said tangent of theta is dealing with the ratio of y over x. All right, but R was okay, but then, we kind of did some problems for this one, and then we went into the next lesson, which is basically introducing us to the unit circle, because, our trigonometric functions are always the same no matter what R was, or x and y, because they're all proportional to each other. But therefore, to make our life a little bit easier as well as the work, we said, well, what if y was equal to r? I'm sorry, r was equal to 1. If r was equal to 1, that simplified things, because instead of saying sine is opposite over hypotenuse or y over r, we could say sine was represented by the y coordinate of sine of theta, and x represented the cosine of theta. So even though tangent of theta is y over x, if now we understand that r is equal to 1, and again, this is proportional, right? R could be a different number. You just, multiply by whatever r is. We'll get to that later. But therefore, since y is equal to sine of theta and cosine, or x is equal to cosine of theta, we can come up with our next identity, which is tangent of theta equals sine of theta over cosine of theta. Okay, so rather than trying to just memorize these identities for all of these, we actually have some names for them. So the first set was the reciprocal identities. And again, we've already kind of talked about how these sides of the triangles or these trigonometric relationships are reciprocals of each other. So it's actually just, now we're just kind of putting them into a nice little platter here so we can absorb them. And, again, this is stuff that we've already covered in this class in our previous chapter on trigonometry. So hopefully with a little bit of practice, this something comes familiar with students. And then comes up to the quotient identities, which is basically, makes sense. Again, if tangent is sine over cosine, since cotangent is the reciprocal, that's going to be cosine over sine. All right, so now I'll get into some problems. And the way that I designed this lesson was basically to try to relate as much of the operations or what we have previously done in our math education to our analytic trigonometry chapter. So for this case, what we're going to do is we're going to multiply the arithmetic expression first, and then we're going to multiply the trigonometric expression. So basically, we're going to apply the operations here with the numbers, and then we're going to apply that to trigonometry. All right, so in the first case, hopefully you guys recognize this is 4 times 1/4, so we know the answer is 1. But again, if we had to multiply a integer by a fraction, we would just change the integer to a fraction, and then you could just multiply straight across, right? So 4 times 1 is 4, over 1 times 4 is 4, and therefore you can see 4 divided by 4 is just equal to 1. Now, in this case, hopefully again you recognize this, that sine of theta times cosecant of theta is, again, it's a function multiplied by its reciprocal, so we know the answer is just going to be 1. But again, if we want to play around with this a little bit, we can use these identities, and this is why I wanted to kind of show students with this, because it's kind of that tricky thing that we're now learning. So you could write this expression in terms of signs. So therefore, you could see that now the signs would divide out and you're left with 1. Or you could write the function, or you could write this expression in terms of cosecants times cosecant of theta. And that'd be equal 1, right? Because the cosecants would divide out. The problem that a lot of students get is they say, well, why can't you do it for both? Well, again, you can, but again, that doesn't help us simplify the expression. Nothing divides out when you do it in this way, right? So again, the goal when you're trying to divide or you're trying to simplify things, we're trying to condense this. So applying the division property, having the same function in the numerator and denominator in this case, is going to allow us to reduce it down to one trigonometric function. In this case, which would be the number 1. All right, so multiplying fractions. So again, when you multiply fractions, you're just going to be multiplying straight across. Numerator times numerator and denominator times denominator. So this one's equal to 1. Now, another way we could do tangent. So tangent and cotangent are nice because you could use the reciprocal identities like we just did, or you could also convert these to quotient identities, which is actually going to be more common that you're going to see, is rewriting these in the quotient identity. And again, you can multiply these straight across, but again, you also see that this is a function multiplied by its reciprocal function, so we know the answer is going to be 1. In this case, again, you could multiply across if you want to, but again, you can see those 4s are going to divide the 1, and you're left with 3. Now, in this case, this is where it kind of comes into tricky, and this is what I was saying tangent. You could rewrite tangent as 1 over cotangent. That's not going to help you simplify anything. You could rewrite cosine as 1 over secant. That's not going to help you simplify anything. So that's why a lot of times that, you're just going to want to play around things. If you don't get it right the first time, that's fine. Erase it and try something else. Here you can see that now I have cosine denominator in the numerator, so those will divide out. So therefore, that's just going to simplify to the sine of theta. Exact same thing that's going on here. You can see these 3s, those will just divide out, so you're left with 1 over 4. So here, again, nothing's really dividing out, so therefore I will rewrite this using the quotient and the reciprocal identity. and now the cosines divide out. So that's going to leave me with a 1 over sine of theta, which I can now use the reciprocal identity again to give me cosecant of theta. Sorry about that. So you can see how you can actually apply, like typically when we are simplifying trigonometric expressions, if we can simplify it down to one trigonometric function, we're going to want to. So typically we're not going to want to leave it as 1 over sine of theta if we can just write it as cosecant of theta. All right, so now the next one is we are going to go ahead and divide our trigonometric trigonometric function. So remember, dividing is the same thing as multiplying by its reciprocal, right? And again, this is something that I, kind of went over with the students. If you did 3 divided by 1/2, that is the same thing as 3 times 2, right? And again, the reason why that works is if we want to get this fraction off the denominator, you're going to multiply by the reciprocal, okay? So you can see now when you multiply reciprocal, that goes to 1, and then you're left with 3 times 2 over 1, which is, again, 6. So a lot of times, at first I show my work. I say, I multiply by the reciprocal, right? And then students would say, okay, so 1 times 4 over 1 is just 4. 1/4 times 4 over 1 is 1, so therefore that gives you 4. And again, we kind of show our work here in this case, but then we just kind of realize we don't need to actually do the work in the denominator if we just multiply the numerator by, we don't need to show this work if we can just do this, right? These both equal 6. This is showing a lot more work than that, okay? But again, let's just plan. Our goal here, if we are taking something, dividing by another function here, if I multiply by the reciprocal, which is sine of theta, okay, sine of theta times sine of theta is going to be a sine of theta squared. Okay, and cosecant of theta times sine of theta, again, it's a function multiplied by reciprocal, it's just 1, right? Now, Dan, technically, we don't really need to show this step. We could just really multiply the numerator times sine of theta and kind of be done with it. Because obviously, that's always just going to be going to 1, right? Dividing by a fraction is the same thing as multiplying by its reciprocal. Now, one of the points that I wanted to make, though, with this problem is how we write this notation. So this is sine of theta squared, right? It's basically sine of theta times sine of theta, and that's how we write it. However, if my students, write it like that, that's not wrong. It's perfectly fine. However, we're really going to see it written like this, sine squared of theta, okay? But the one mistake that students will make is they will write it like this, sine of theta squared, okay? And basically what that's saying is that is taking the sine of your angle squared. Well, it's not your angle is being squared. It's the function's being squared of your angle theta. So we just want to be really careful. These were the 2 proper notations that are acceptable. But again, a lot of times students will be in a rush or they'll be confused or, stressed, whatever, and they'll make a mistake and they'll write it incorrectly there. All right, so basically what I just kind of did is, for these problems, we just kind of went into, divide. Instead of dividing, we actually just multiply by its reciprocal. Now, in this first problem, though, we actually have something even easier. We notice that it's a fraction divided by itself, so that's just going to be 1. Right? I don't need to go through any of this stuff, guys. Cotangent theta divided by cotangent theta is just 1. Done. Now in this case, again, if you have 3/4 divided by 1/4, again, we can just rewrite this as 3/4 times 4 over 1, right? Why do division when we can just write it as our multiplication of the reciprocal? And therefore you can see that answer is just 3. So again, what I'm going to do here is, since I'm more familiar with that multiplication, I kind of like that a little bit more, and it's a little bit easier. It's not too bad. I'm just going to write this as cotangent of theta times the reciprocal of cosine, which is secant of theta. Now again, I will simplify this. So this is going to be cosine of theta over sine of theta times 1 over cosine of theta, which equals 1 over sine of theta. Oops. All right, which we know is going to be cosecant of theta. And then this one, I kind of ran out of space here. I guess I didn't really give myself a good idea here. So this is, I'll write this up. Let's squeeze this in there. That's going to be sine of theta times cotangent of theta. So it's sine of theta times cosine of theta over sine of theta. Those will divide out, leaving me with a cosine of theta. Okay, so now into the next set of identities is the even and odd identities. Now, these identities are actually fairly basic. When students actually, and I forgot to actually correct these, thankfully, I went through this. So yeah, these are actually my old notes. I gotta go back in and fix those. So this actually looks a little confusing to a lot of students when they first see them, but it's actually fairly basic. And the main important thing that I wanted my students to come away from this is understanding that the cosine and the secant of a negative angle, right, is going to be the same as the positive angle. And again, this makes sense. And what I did is I gave my students kind of two examples. So I said, all right, why don't we look at the cosine of pi? And if we look at the unit circle here, cosine of pi is down here. That coordinate point is -1, 0. So the cosine of pi is equal to -1. Well, what about the cosine of negative pi, right? That's basically what we are doing over here, is we're doing the cosine of pi, cosine of negative pi. Well, negative pi is right there, right? And you can see that's -1. So you can see these two work with each other, or they're exactly the same. On the contrary, what about the sine? What about if I was looking at the sine of the angle compared to the positive sine of the angle, or the sine of a negative angle compared to the sine of the positive angle? So in this case, let's look at the sine of pi halves. So the sine of pi halves is right there, which is the coordinate point 0, 1. And the sine of negative pi halves, so that's 1. Sine of negative pi halves is going to equal -1. So you can see how when it's a negative angle, it's still the same value, but it's negative. And that's going to work for tangent, cosecant, and cotangent. And again, the reason why that works is because of symmetry of the graphs. Cosine and secant are even functions. They are symmetrical about the y-axis, whereas sine, cosecant, tangent, and cotangent are symmetrical about the origin. So what I also did is I just kind of quickly showed my students in the calculator, and we have a little time, so why don't we just go and take a look at this really quick on this Desmos graph I created. Okay, so now to Desmos. Again, you can see here, here's the sine graph. Actually, no, let's not do sine. Let's do cosine first. So here's the cosine graph. And again, if you remember what I talked about is cosine of pi is the same thing as cosine of negative pi, right? You can see that cosine of pi and cosine of negative pi both have the point of -1. And again, this works for secant as well, right? You can see that these two are all produce the exact same points. So it doesn't matter whatever the positive angle, you can see that there's symmetry of the negative angle is going to have the same y coordinate. And again, that's because the cosine and the secant function are even functions. Whereas when we look at the odd functions, like sine here, that when I have, pi halves, that was 1. And then when I say what is sine of negative pi halves, that's going to be -1. So whatever the positive angle is, if it's, whatever that sign is, the negative angle is going to be the negative sign, right? And those are flipped. For instance, here, 3 pi halves is -1. So if I do -3 pi halves, that should be +1. And look at this, and you can see. Okay, and again, that's because the sine graph, the tangent graph, the cosecant graph, and the cotangent graph are all symmetrical about the origin. You can kind of see here. You can see how the graphs, you can see how that reflection of the sine of negative x, that reflection about the y-axis, since it's an odd function, you can see that whenever blue is positive, the red is negative. Whenever the red is positive, the blue is negative. So you can see that kind of relationship and how it works. All right, so now let's go and look into our next identity. All right, so after the even odd identities, the next identity we're going to tackle is the cofunction identity. Now, if students thought that the even odd identities looked confusing and they weren't going to memorize them, they usually get a little overwhelmed looking at the cofunction identities. But there's really some important points that I want students to really make. Again, for the even odd, we looked at the graph. We looked at the transformations, right? These graphs are being reflected, or all that negative was a reflection about the y-axis. So a couple points here. Really what we're doing is we're just transforming the graph, right? If I have the sine graph, if I have pi halves minus x, like what is that doing to the graph? So let's actually look at it. Like if I had y equals, if I was actually going to graph sine of pi halves minus x, what is these transformations going to be doing to the graph? Well, let's go ahead and rewrite this. So if we were going to actually identify these transformations, we would flip the negative, we'd flip the x in the pi halves, and we'd factor out the negative. So therefore, I'd be left with a negative x minus pi halves. So you can see what we're doing for each one of these graphs is we're actually reflecting about the y-axis, just like the even odd graph, but then we're shifting the graph pi halves. Now, if you are going to apply all these transformations to sine, there's only one graph or one other function that graph will look like, and that is cosine. It's never going to look like tangent. It's never going to look like cotangent, cosecant, or secant. Okay, so that's why what we call is the sine and cosine. So I can say sine of x and cosine of x are what we call cofunction identities. They're cofunctions of each other, all right? And that is the same thing with tangent and cotangent, as well as cosecant of x and secant of x. Okay, because if you apply transformations to one, you're only going to get the other function. The other thing that's important is, again, a lot of times pi half, sometimes you might see this as in degrees. So just remember that 90 degrees minus x is also going to be that cofunction identity. So just real quick, I just want to kind of show my point to my students, just looking at the decimals again. Okay, so going into the graphs now again, if we look at this, like here's the sine graph, right? And here's the cosine graph. Now a lot of students say, well, why couldn't you just do an identity where you're shifting the sine graph to the left to get to cosine? And that's true. You could do an identity. You could do, sine of x plus pi halves to give you cosine. The problem is that doesn't work the other way. That you have to now shift cosine to the right to get to sine. So the only one that works here for these identities is when you actually apply these identities here. So again, if I look at this, you can see that, you can see that when I applied the reflection and the shift, you can see I get the cosine graph. Or if I did it with these two, with cosine, and then if I apply those transformations, you can see now I get this sine graph. So what's nice about this is by applying these transformations, they give us the other function. Now again, looking back at this, sine and cosine are what we call cofunctions of each other. They're never going to look like tangent, right? They're never going to look like cotangent, cosecant or secant, right? So they don't have any of those properties. And that's kind of the same thing. You can see how I kind of group them together as their cofunction identities. These graphs, these graphs are related to each other by transformation. And that transformation is reflection about the y-axis and shift pi halves to the right. So, and again, you can see here by this cotangent how this doesn't work shifting left to right. That's why you have to have that reflection to provide this. So again, it works for no matter what two functions that you're dealing with. You can see that's going to produce the same graph. These two are going to produce the same graph. And that works for, again, for these functions as well. So you can see same graph. And then same graph. But again, like you can see how these, like you're never going to take this graph and then somehow get tangent or somehow get the sine graph, right? So that's why if you can just remember that how those graphs or those functions are related, their graphs are related, then you can remember which functions are cofunctions of each other and then easily apply those identities. Okay, so now let's get into some examples of simplifying. So basically when you see, these identities, the first thing you're going to want to do is apply the identity, like simplify it before you do any algebraic operations. So if I see sine of negative x, I'm just going to rewrite that as the sine of x. The cosine of pi halves minus x, you can see I'm applying the cofunction identity. So that's going to be not cosine, that's going to be a sine of x. All over here, I have sine of pi halves minus x. Again, that's a cofunction identity. That's going to give me a cosine of x. And then I have tangent of negative x, which again, I'm going to want to make sure I rewrite that with parentheses of a negative tangent of x. The next thing now, again, because if you don't use parentheses, then people are going to, then it might be confused that that is going to be a subtraction problem, right? But you're multiplying by negative. And again, if you had like 1 times negative 2, that's the same thing as negative 1 times 2. So a lot of times it's just easier to put the negative in front. So if we do that, we have a negative sine squared of x all over a negative cosine of x times tangent of x. Now again, we can't really simplify anything in this denominator yet. So therefore I'm going to rewrite tangent as sine over cosine. The negatives, let's just rewrite that. So it's a negative sine squared of x all over a negative cosine of x times sine of x over cosine of x. So here you can see that now my negatives are going to turn to a positive, and I have a cosine of x divided by cosine of x is a positive. Then I just have a sine squared of x divided by a sine of x, which you can just see is, kind of like an x squared divided by x. You can see that is just going to give us a sine of x. Okay, so in our examples, and then I just kind of worked with my students is just again kind of apply these same operations here. So in this case, I'm going to kind of apply the operations at the same time to simplify this. So we have negative sine of x, cotangent of x is going to be a cosine of x over a sine of x. Those divide out, so that's going to leave me with a negative cosine of x. Cotangent of x using the cofunction identity, right? Cotangent can only look like tangent of x. Cosecant, I'm going to rewrite that in terms of sine. Okay, and then tangent, I'm going to rewrite that as a sine of x over cosine of x times 1 over sine of x, which I don't really like going horizontal after you're doing vertical. You can see, though, that's going to be a 1 over cosine of x, which is just equal to a secant of x. For next one, a secant of negative x. Remember, secant is even, so therefore that is just the same thing as secant of x. And then cosecant of pi halves minus x, using the cofunction identity, that's equal to secant of x. So again, secant of x times secant of x is equal to a secant squared of x. Next example, again, cosine is even, so therefore that's going to be a cosine of x. Cosecant is odd, so that's going to be a negative cosecant of x. All over cotangent, which again, I can just, I'll just go ahead and rewrite that. Actually, you know what? Yeah, let's just rewrite that as a cosine of x over sine of x. And the reason why I'm just writing that out is, again, I can say, oh, instead of dividing by this, why don't I just multiply by its reciprocal, right? You could just multiply by tangent, but again, what is multiplying by tangent? Sine over cosine. So I can put the negative all the way in front here. So I have a negative cosine of x. I'll rewrite cosecant as 1 over sine of x. And then I have sine of x over cosine of x. Now again, I'm showing a lot of my work here. But again, like the faster, the more you get with this, the more examples you do, the faster and least amount of steps that you'll have to go ahead and apply. But you can see here the answer is -1. For the next example, again, we have a negative tangent, so I'm going to just put that in front. So I have a negative cosine of x. I'll put that tangent here as a sine of x over a cosine of x. Actually, you know, let's just, well, I'll put that, I don't want to confuse too many people here. I'll just put the negative up top. Again, like, where do you put the negative, right? Well, again, you could put the negative, you know, I just think that's confusing. So let's just go ahead and rewrite that as a negative sine of x over cosine of x. But in reality, guys, you could put that in the to sine or to cosine or put it in front. And then using the reciprocal function of cosine, that's going to be the sine of x. So really what I'm multiplying is the reciprocal, which is cosecant, or you could just think of, you know, 1 over sine of x. Right? So if you multiply by 1 over sine of x, again, you can see we have the cosines, one's in the numerator, one's in the denominator, and then we have a sine, one's in the numerator, one's in the denominator, and obviously those are all going to divide out, just leaving us with, again, another answer that's -1. All right, on to our last example here. We have cosine of pi halves minus x. That's going to equal a secant of, not a secant of x. What am I doing? Cosine can only look like, when you apply transformations, cosine's only going to look like sine. Okay? And then we have that times cosine. And then instead of, be careful here, though, let's go ahead and rewrite this as equal to tangent of x. Then instead of dividing by tangent, we can multiply by the reciprocal, which would be cotangent. So that'd be sine of x times cosine of x times cotangent of x. Well, again, we don't need to write cotangent of x because that's not going to help us simplify anything. We could write that as cosine of x over sine of x. Now you can see that the cosine squared, the sines will divide out. So therefore, that's going to leave us with a cosine squared of x. All right. The last identity that we need to cover before we get into all of the fun of simplifying is the Pythagorean identities. Now, again, I made some mistakes here when uploading my notes, so I got to go and fix that real quick. Apologize. These should all have x's here. Oh, did I go and do that? I think I forgot. No, I did the even odd. I think I got those right, though. Yeah, it was just the even odd. Okay. All right, so those are supposed to have x's with them. I didn't get to them in time. Now, again, where do these Pythagorean identities, come from? Or how can we, if we were given one, how can we go ahead and find the others? Well, remember, where we left off with our triangle was we had a triangle that looks like this, right? Here was our theta, right? And then we said this was our x, this was our y, and then we said this was 1. Well, again, remember that x equaled the cosine of theta, and y equaled the sine of theta. So if that is the case, then we could draw our triangle like this. Sine of theta. Here's theta. That's not sine of theta, that's cosine of theta. Geez, I'm going crazy. So that's cosine of theta, sine of theta, and that's 1. And of course the Pythagorean identity is going to work. So we'd say cosine squared of theta, or Pythagorean theorem, plus the sine squared of theta is equal to 1. Now the important thing is, well, where does the other function, like where do those other trigonometric functions come through? Well, again, as long as we apply the same operation to every single term inside of an equation, we are going to produce what we call an equivalent equation. So here is my first identity, right? Well, what happens here if I take cosine squared of theta plus sine squared of theta equals 1? What happens if I divide everything by cosine squared of theta? Oops, not that way. Similarly, what happens if I take this trigonometric identity, or this Pythagorean identity, and let's say I divide everything by sine squared of theta? Okay, here I get 1 plus tangent equals 1 over cosine is secant squared of theta. Cosine squared over sine, and again, I should probably slow down. Cosine over sine is, we know that is going to be cotangent. So cosine squared over sine squared is just going to be cotangent squared of theta. Sine squared over sine squared is just going to be positive 1. And 1 over sine is going to equal cosecant. So 1 over sine squared is going to be cosecant squared of theta. So you can see where the rest of them come from, or how they were created. All right, so now we got some more operations that we're just going to go ahead and apply. So again, remember, when you are applying multiplication, we need to apply distributive property. Now, hopefully you recognize here, this is a minus b times a plus b, right? The first two terms are the same, last two terms are the same. So therefore, you know that that simplifies to a squared minus b squared, which is the difference of two squares. But again, just to kind of point out, if you forgot all of that, remember you could multiply everything out. X times x is x squared, x times 1 is x times negative 1 is negative x, and negative 1 times positive 1 is a negative 1. You can see my middle terms though, they add to 0, so we're just left with an x squared minus 1. But the reason why I think that's very important is because nobody really wants to multiply this out. You hopefully recognize again, oh, this is another difference of two squares. So why go through all of this step of multiplying everything out, dividing out, adding up the middle terms, when you can just apply the squared first two terms minus the last two terms squared. Since they're both the same, if this is just going to be sine squared of x minus 1 squared, which is just 1. Then you could also see that based on our Pythagorean identities, this is actually going to equal our cosine squared of theta. But it's not exactly as you would think. So let's go back to our identity. Cosine squared of theta plus sine squared of theta equals 1. Now, if I wanted to get sine squared of x, in this case we have x instead of theta, but if I wanted to get sine squared of x minus 1, I need to subtract a 1, right? So I have cosine theta of theta plus sine squared of theta minus 1 equals 0. Well, again, we're trying to solve for this, so I'm going to subtract a cosine squared of theta. So just by using a little bit of some algebra, just manipulating this equation, I get sine squared of theta minus 1 equals negative cosine squared of theta. So if I needed to simplify this a little bit further, then I could rewrite this as one single trigonometric function, negative cosine squared of theta. And that's something that we want to keep in mind, especially based on whatever the directions are, as well as what might be a multiple choice. So I'll be practicing some of that as we get through some of these examples, trying to simplify it a little bit further. All right, so then I gave my students again the same thing. I said, all right, let's go ahead and multiply these out. So again, recognize the difference of two squares. That's going to be 1 minus x squared. So in this example, again, we notice the 1 minus x squared. This one becomes 1 minus sine squared of x. Hopefully, again, looking at that Pythagorean identity, you recognize this to be cosine squared of x. Over here, you're just going to apply distributive property. That's x squared plus x. So again, distributive property, this becomes sine squared of x minus sine of x. Now, the one big mistake that students still forget, remember x plus 1 squared is not x squared plus 1 squared, right? This is x plus 1 times x plus 1. you have to go back and do FOIL. But hopefully you recognize that this is a perfect square trinomial, right? By binomial expansion, we actually should remember how to expand something squared. So this becomes x squared plus 2x plus 1. And the nice thing that actually I want students to start taking away with, or start making the connection, is, you know, again, the reason why I go through this is x plus 1 squared, okay, and then sine of x plus 1 squared. Well, it's really the same thing. The only difference is instead of the function x, I'm using the function sine of x. So if I actually just multiply things with x or apply my operations with x, I can just substitute in sine of x in for my x. So therefore, this becomes 2 sine of x plus 1. And you can kind of see now how that works and relates to each other. All right, so now let's go and get into adding and subtracting some fractions. So in this case, we're just going to add and subtract some fractions, and this is from our chapter on rational expressions. And just remember, when we have to combine fractions, that we are going to obtain common denominators. And if the two functions do not have a denominator in common, or they don't divide into one another, then the easiest and fastest way to find a common denominator is just to multiply them. So the LCD in this case is just going to be x plus 1 times x minus 1. So all I'm going to do is multiply by x plus 1 over here, x plus 1, and here I'm going to do x minus 1 times x minus 1. So now they'll have the common denominator of x minus 1, x plus 1. So I'll have an x minus 1 plus an x plus 1 all over an x minus 1 times an x plus 1. Okay, and now I can apply my operations to my numerator. So I have x plus x, which is 2x, negative 1 plus 1 is 0, so therefore I'll be left with a 2x all over an x minus 1 times an x plus 1. So you can see here, it's really the same thing. Now, I don't even want to think about trying to divide signs and like numbers and variables. It's like, that looks weird. But you could identify this and say, oh, well, the LCD then is just going to be the product of 1 plus sine of x times 1 minus sine of x, right? So therefore, I'm just going to multiply by 1 plus sine of x over 1 plus sine of x. Whereas over here, I'm going to multiply by 1 minus sine of x all over 1 minus sine of x, right? So now my common denominator, now I could have simplified this a little bit further. We recognize that to be x squared minus 1, right? And this one we recognize to be 1 minus sine squared, which is kind of important. So when we multiply this, I get 1 minus sine of x plus a 1 plus sine of x all over, in this case, I'm going to have a 1 minus sine squared of x. Now, it's important for us to look at this. So we can simplify this. We can see the signs here are going to divide out, and I have 1 plus 1, which is 2. So that becomes a 2 over 1 minus sine squared of x. Now again, using my Pythagorean identities here, I recognize 1 minus sine squared of x is equal to cosine squared. And 2 over cosine squared can be written as secant squared. So this could be 2 secant squared of x. So you can see how you can play around with this. You can keep on simplifying that a little bit further down, a little bit further down, a little bit further down. All right, so now let's get into adding and subtracting some numbers. Now this one's a little bit more basic. These are the problems I gave my students here to work with some numbers, right? And so just a good review that remember that 1 over 4 plus 4 over 1 is actually going to be, you got to get common denominators, right? Now 1 actually evenly divides into 4, so therefore I don't need to multiply, do anything to the left-hand side. I just need to multiply here as 4 over 4. So I get a 1/4 plus a 16/4, which equals a 17/4. So again, here's the same case here. I'm going to multiply by sine of theta over a sine of theta. Well, a sine of theta times negative sine of theta is going to be a 1 minus sine squared of theta all over a sine of theta. And that can be simplified again to a cosine squared of theta all over a sine of theta. Now again, some people might say, well, that's going to be fairly simplified. Just want you to be aware though, that also could be rewritten as a cosine of theta over sine of theta times a cosine of theta. right? You can break up cosine squared of theta times cosine of theta times cosine of theta. And the important thing is, the reason why that's important is because that can simplify cosine over sine is cotangent of theta times cosine of theta. So you can see how that problem can be just simplified a little bit further and a little bit further down. Actually, I'll just write it over here. That's going to be a cotangent of theta times a cosine of theta. Now, the reason why I'm writing it down there, because this next problem is fairly simple. This one's not as bad here, right? You can see this example is going to be 1 over cosine of theta plus 1 over cosine of theta. Well, again, since they have the same denominator here, we can just add the numerators, right? Over here, you get 2 over 4. But again, just remember you can always need to simplify that to reduce to 1/2. Whereas here, this is just going to give us a 2 over cosine of theta, which again, we can rewrite not as a fraction to give us 2 secant of theta. All right, and the last but not least here, kind of like the example problem that I gave, but rather than dealing with variables, if I gave you something here with numbers, to get common denominators, I would multiply. You can see my LCD in this case is going to be 12. So I'd multiply by a 3 over 3 and a 4 over 4. So therefore, 3 over 3 times 3 over 4, that's going to be a 9 over 12 plus a 16 over 12, which equals a 25 over 12. So in this case, the same thing. Sine doesn't even divide into cosine, nor does cosine divide into sine, right? So therefore, I'm just going to multiply each other to give me a denominator. So I'll multiply by sine of theta over sine of theta, cosine of theta times a cosine of theta. Here I get a sine squared of theta plus a cosine squared of theta all over a sine of theta cosine of theta. Now again, one thing we recognize here is sine squared of theta plus cosine squared of theta is going to add to 1 here. So it's going to be 1 over sine of theta cosine of theta, which could simplify one more time as the reciprocal identities, using this to be cosecant of theta over secant of theta. All right, getting into the next one here is simplifying fractions. So if you remember, this was the one that we kind of covered with complex fractions. A lot of students really struggle with this, again, with our rational functions. But just remember, when we have fractions in the numerator and the denominator, our goal is really just to get rid of our fractions. So the easiest thing that we kind of developed here was to multiply by the LCD. In this case, the LCD of all my denominators is 3. So when I multiply everything times 3 in this case, what I end up getting is 3 plus 2 divided by 3 minus 2. Now I just basically have one fraction, a numerator and a denominator, where now I can simplify this to give me 5 over 1, which is 5. You can see that is a lot easier to work with rather than the original problem. Now in this next example, this is kind of my introduction, and sometimes actually in this class I kind of introduce students over here to it. But when you're trying to simplify fractions and you're saying, well, or simplify something, you might not recognize the fractions at all. Like, where are the fractions here? So again, we can use our quotient as well as our reciprocal identities to write everything as a fraction, right? Because right now, I can't multiply everything by a given function to divide anything out. So what I'm going to do in this case is I'm going to rewrite everything in terms of sines and cosines. So I'm going to rewrite this as 1 over sine of theta plus cosine of theta over sine of theta divided by 1 over sine of theta minus cosine of theta over sine of theta. Now you can see here that everything is being divided by sine of theta. So now it's kind of similar to this last example, where now I can just multiply everything times a sine of theta. Okay, so a lot of times if it's something does not seem obvious, the best thing would be to write everything in terms of sines and cosines. So now when I multiply everything times sine, I get sine times 1 over sine is just going to equal 1 plus cosine of theta times over 1 minus cosine of theta. Okay. I guess I didn't even plan on getting to that point. Crap. All right, well, I created this one. I didn't go through this one with my students, so obviously that was I didn't really mean to get to that point. So let's actually come back to this problem. So it says not as a fraction, which I have a way to show you how to write this as not as a fraction. But for right now, we don't have a way. So let me kind of work to our next example, and then we'll come back to this one. So the examples I gave to my students, though, were some problems that looked kind of like this. Okay. So again, using the same idea here, if I was going to multiply by 4, or if I wanted to undo divide by 4, I would get 4 minus 1 all over 4, that's going to be 1. So that just gives me a 3, right? So again, here it might not be obvious as far as what my common denominator is. So I'm just going to write everything in terms of sines and cosines. So this would be 1 over cosine of theta all over 1 minus cosine of theta. So therefore, I'll just multiply everything now by the common denominator, or cosine of theta. And that gives me a cosine squared of theta minus 1 over 1. And again, remember cosine squared of theta minus 1, that's going to equal a negative sine squared of theta. Let's go ahead and work into this one because I did rearrange these. The next one, you can see the common denominator is going to be the product of 3 times 3 and 4, so which is going to be 12. So if you multiply everything times 12, 3 divides into 12 4 times. 4 times 4 is 16. 12 times 3/4, 4 divides into 12 3 times. 3 times 3 is 9. And that goes in 4 times plus 16. So therefore, I'd have 16 over 25. Okay, so again, same kind of idea here is let's rewrite this not with tangent and cotangent, but in terms of sines and cosines. So therefore, this would be cosine of theta over sine of theta divided by a sine of theta over cosine of theta minus a cosine of theta over sine of theta. So again, you can see that they do not have any, their denominators, or the common denominator is going to be sine times cosine. So I'm going to multiply everything times the sine of theta, cosine of theta. And when I go ahead and do that, I get the sines will divide out. So I'll be left with a cosine squared of theta. All over here, the cosines divide out. So I'm left with a sine squared of theta. I keep on forgetting to change that problem. That was a plus. Sorry about that. That's a plus. And then the sines divide out here, and that's going to be a cosine squared of theta. So therefore, the reason why I need to be a plus is because you can see that sine squared plus cosine squared is equal to 1. So therefore, you're just left with a cosine squared of theta. Okay, now into the middle one, which is kind of helps us back into that original problem. How do I get rid of a radical? Well, again, we talked about, previously getting rid of radicals was, multiplying by the conjugate, right? And if you remember from Algebra 2, we would multiply by 1 plus the square root of 3 in our problem. So when I multiply by 1 plus square root of 3, what happens is I apply distributive property in the numerator. So I get a negative 2 minus 2 square root of 3. The denominator, you recognize that's a difference of 2 squares. So that gives us 1 minus 3, which now can be simplified to a negative 2 minus 2 square root of 3 divided by negative 2. And I can distribute that to both of them to be a 1 plus the square root of 3. And that's something we're going to cover in this class. Now, obviously, for a trigonometric function, we're not trying to eliminate a radical. There are no radicals in this problem. But if we kind of use this idea of multiplying by the conjugate, what we are going to create when we multiply a trigonometric expression like 1 minus sine of theta or 1 plus sine of theta by its conjugate, what we do is we create a Pythagorean identity. So that's why it's helpful to multiply by the conjugate. So in this case, I'm going to multiply by 1 plus the sine of theta. 1 plus the sine of theta. Okay, again, that is the conjugate of my expression 1 minus sine of theta. So when I do that, I get a cosine squared of theta times a 1 plus a sine of theta. And that goes all over. Let's see here. This becomes a 1 minus sine squared of theta. And again, this is what we recognize. This 1 minus sine squared of theta, that is equal to cosine squared, right? So this becomes a cosine squared of theta times 1 plus sine of theta divided by a cosine squared of theta. So that's equals 1 plus sine of theta. So you can see how that is helpful, how that will help us simplify things. So let's kind of come back up to our original problem here. So if I wanted to get rid of cosine, or if I wanted to, eliminate this fraction, I want to make this, one single trigonometric function here. So I'm going to multiply this by 1 plus cosine of theta. Now, I don't think this is going to be eliminating my fraction per se, because this is just going to give me sine. But again, this would at least be, 1 plus 2 cosine of theta plus cosine squared of theta. Okay, yeah, I created this, and I guess I didn't check my work on that one because that one's not really helping me out here. So that'd be 1 minus cosine squared of theta, which is going to be just giving me sine of theta, which is cool, but that doesn't eliminate my fraction. So I'll have to come up with a new problem. So I apologize for that. I didn't have time to cover that one in class. So that was actually my first time covering that problem. I thought I worked through it on there, but I guess I didn't get it all the way in there. So I guess what probably would have been better is just maybe even write that as 1. Yeah, either way. Okay. Yeah, that's the same as that one. Okay. All right, so onto the last set is going to be factoring, right? And remember factoring algebraic expressions, basically the same idea we are going to apply to trigonometric expressions. So, a lot of times once you get into trinomials, people totally forget what we learned with binomials. Whenever you're looking at an expression, algebraic or trigonometric, when you recognize that they have, common elements, think factoring. In this case, you can see that we can factor out a common element of x. By factoring out x, I'm left with a 2x plus 1. Again, if you're not sure that I just did that correctly, multiply it back. X times 2x and x times 1 gives you 2x squared plus x. So in this case, you can see that I have a common element of sine of x. So by factoring out a sine of x, I'm going to be left with a 2 cosine of x plus 1. All right? Sine of x, cosine of x plus 1. Okay, now let's go and take a look at the factoring of expressions. So again, now we're just going to work through the same thing. And again, this is that going back to, if you remember that relationship I talked about, is you can apply the operations with x and then just go and apply them to the sine of x or to your trigonometric functions. So in this case, we're basically saying, again, whenever you're looking at trinomials, try to think of what two numbers multiply to give you 1, add to give you 2. So are your middle terms. So this is x plus 1 times x plus 1, which can also be written as an x plus 1 squared, right? So my basic idea is, guys, this is a trigonometric equation that's a trinomial. So you can see that we can rewrite this as, or if you have this, basically what we're saying is, what two terms multiply. Remember, the first two terms always multiply to give you our first term. So like, what times what is going to give you a sine squared of x? Oh, that's just going to be a sine of x times a sine of x, right? And then you can see here, this is just a replacement of the function. So this is going to be sine of x plus 1, sine of x plus 1, which is a sine of x plus 1. Whenever I have a binomial, a quadratic binomial, I'm thinking difference of two squares. In this case, you can see that, that can be written as an x minus 1 times an x plus 1. So again, just replacing my x with my trigonometric function, I can write this as a cosine of x minus 1 times cosine of x plus 1. So whenever students are having trouble, I always say go back to x's, go back to y's. Do what you're most comfortable with. Especially a problem like this. Like this would be really confusing first-time students, take a look at it. But in reality, if you just kind of look at this, if you factor this, if you know that's a trinomial, all right, it's a quadratic trinomial. That means it's going to be factored into a product of two binomials. The first two terms are going to multiply to give me 2x squared. All right, well, that has to be a 2x, and that's going to be an x. The next two terms are going to multiply to give me a 1. So that is going to be, 1 times 1 or negative 1 times negative 1. But they are going to, the inner and the outer are going to add to give me a negative 3. Well, therefore then, since these two are positive, that means these two have to be negative. So I really have no other choice. It has to be 2x minus 1 and x minus 1. There's no other option, no other, possibility. And again, if you get stuck, try it. Try it, and then multiply it out and see again if it works. Like you can see, 2x times x gives you 2x squared. Negative 1 times negative 1 gives you positive 1. And negative 1 times x gives you negative x. And 2 times negative x gives you negative 2x. Negative x plus negative 2x is a negative 3x. And then to rewrite this with my trigonometric functions, I will just replace my x with my sine of x. Okay. And there you go, ladies and gentlemen. That is at the end of this lesson. So I hope you understood some concepts. This is not something that comes easy to a lot of students. So my best advice is to just keep on practicing, keep on working at it. It is something that you will get better at with some practice and with some time. So, however, if you do have any kind of comments or any other questions, feel free to always add them down in the chat below. And I really do appreciate you taking the time, and I look forward to seeing you on the next video. Cheers.